Hello and welcome. In this video we're going to talk about proof by mathematical induction, or PMI. So first we assume that for our proof that for the first term P of 1 is true, and that wherever it's true for some k, it follows that k plus 1 must also be true. If that happens, then the sentence, or what we're trying to prove, P of n is true for all natural numbers. So there are some steps that we take when we're trying to prove by mathematical induction. The first thing is you got to state what you want to prove. So that's the first step. The second step is you want to show it's true for the first case. Usually this is n equals 1, but sometimes it's n equals 3 or n equals 5. And you work one side and then you work the other side and then you show it's true. Because there's always two sides to this. Sometimes we have equality and sometimes we have inequalities. Our third step is to assume, or by assume that it's true for k, or in other words, we're at the induction hypothesis step. We let n equals k be true for some k. Step 4 is we want to show that it's true for n equals k plus 1, and that will hold true for all k. Typically, we'll work only one side of whether it's an inequality or if it's an equal sign. The last step is rewrite the words, the final statement. We'll write the words, quote, by the principle of mathematical induction, we have that whatever it is we're trying to prove is true for all whatever it is that we're trying to prove. So let's go ahead and start trying some of these. Let's take a look at our first example here. So we want to prove for all natural numbers n that if I add them all up, that I can add them all up individually, or it would equal n plus 1 over 2. So as an example, if I want to add up the first 7 numbers, I can add up all the first 7 numbers, 1 plus 2 plus 3 all the way up to 7, or I can use this formula that is 7 and then 7 times 8 all divided by 2. So that's the first step. We're going to state what we're trying to prove. The second part is we're going to show it shows that it holds for our very first case, which is n equals 1, because that's our first natural number. So we let n equals 1 and we look at the left-hand side, which is just 1. And that comes from right here. That's our very first term, so that is just 1. And we look at our right-hand side, and the right-hand side is this. So we're going to put 1 in there. So we have 1 times 1 plus 1, which is 2. So 2 over 2, which is 1. Since the left-hand side does match the right-hand side, then we know it holds true for our very first case, n equals 1. The next thing we're going to do is assume, this is our third step, assume that this holds true for some value k. So in other words, I have 1 plus 2 plus all the way up to k is equal to k plus 1 divided by 2 is true for some k. And all we are doing right here is that we are taking our original one, original value, or our original equation that we wanted to prove, which is this, and we're just replacing wherever we see n, we're going to replace it with k here, here, and here, because that's where I had n. Now we're going to assume that's true for some value k. Then we're going to say, this is our part 4, and this is where our algebra skills, if we're rock stars at algebra, this will be easier. If we forgot some of our algebra and we need to refresh, this will just be a little bit harder. Not impossible, just a little bit harder. So the first thing we do is we say let n equal some k plus 1. So we go back up to our very first part 1, which again, let me just go ahead and erase some of my writing here. So we're going to just look at what we had before. And wherever we see n, we replace it with k plus 1. So we replace this n right here with k plus 1. Replace this n and this n with k plus 1. So that's where this k plus 1 comes from. And that's where this k plus 1 comes from. And that's where this k plus 1 comes from. Now notice, k plus 1 is the next term in the series. That means the previous term must have been k. Now I didn't do that on my part 3. I could have done that. I could have just squeezed in right here if I wanted to. I could have squeezed in k minus 1, so I'd have gotten the term prior to it. But we're assuming that's true for some k. What we're trying to prove now, this is true for some k plus 1. So let's work with the left-hand side because it has the most terms. So the left-hand side is the 1 plus 2 plus all the way up to k plus 1. So if I take a look at that first grouping, 1 plus 2 plus all the way up to k, then 1 plus 2 all the way up to k, because we assumed it was true for some value k, that 1 plus 2 plus 3 all the way up to k can be replaced with k plus 1 over 2. So then what we really have is the first terms, 1 through k, can be replaced with k plus 1 all over 2, and then we still have the k plus 1, which is what we were hoping to prove. Now what we're going to do on the next step is we're going to make a same common denominator. So I'm going to take the k plus 1, and it is all over 1, so I'm going to put it over 2, and the way I do that is I multiply the numerator and denominator by 2. That way I can go ahead and add them. So now I have k plus 1 times k over 2, and then I have 2 k plus 1 divided by 2. These now have a same common denominator, so I can add the 2. So I end up with k plus 1 times k plus 2 all over 2. Now remember, my eye on the prize is, let me go ahead and erase just a little bit up here. My eye on the prize is this, over here, is on the right-hand side. That's where I'm hoping to get to, is this right-hand side, right here. So that's my goal, that's my eye on the prize. This is where I'm hoping to get to, right here. This is it. This is my goal. I'm almost there. So now what I'm going to do is I'm going to go ahead, and here what I did was I said that 2 is the same thing as 1 plus 1. That means k plus 2 is the same thing as k plus 1 plus 1. And then that gives me right here the part that I need up here. Okay? So by manipulating just the left-hand side, I have the right-hand side. Because the left-hand side is equal to the right-hand side, then my equation that I was hoping to prove, 1 plus 2 plus 3 all the way up to n plus 1 divided by 2, holds for some n equals k plus 1, assuming it holds for n equals k. So then on my next step is I just say, by the principle of mathematical induction, we have that 1 plus 2 plus dot 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 n plus 1 is equal over 2 is true for all natural numbers. I'm going back to show that what I started out with I'd hoped to prove, I did prove. Let's go back and discuss this from the beginning of what I did and what I expect to see on all proofs of mathematical induction for the most part, and what you're going to see on all proofs of mathematical induction for the most part. So let's go back up to the top here. There are certain things that's going to be in every proof by induction, whether you see it through me or you see it on your homework, or you see it on YouTube, or however you see it, that they're pretty much all going to have it. I'm going to highlight that, or I'm going to underline it in green, so that when you're doing your homework, you pretty much just write that part of it. And then whatever it is that you need to add is the parts that I'm going to underline in red. So for the very first one, that this is whatever it is you're going to prove. So you're going to just write that on your piece of paper, or you're going to write that on your homework, because it's going to have something that says show that for all natural numbers n, 1 plus 2 plus all the way up to whatever is equal to n plus 1 over 2. So that's the part that you put in the very first step. Okay? The next part that is true for all of them is this, right here. Let n equal. That let n equal, that's going to be true for every single one of them. So let n equal. It's going to tell you where to start. So Before, it's going to tell you, show that this is true for n equals 1, or n is greater than 5, or n is greater than 10. So the part that you're going to add is just this part right here, n equals, okay? The next part that's going to be true that you're going to write for all of them is you're going to say, then the left-hand side. Then you're going to work the left-hand side, and that part in red I'm underlining is what you personally add. And you're going to work the right-hand side. And again, this part in red is the part that you add. So everything that I'm underlining in green, you can see almost on every proof. It may not exactly be verbatim, but it's going to be on almost every single proof. And then you're going to see this part. Since this and this holds true, and all the way up to for some n, the only thing you have to put in that's going to be different each one is whether that's an equal sign or an inequality sign, and where you started. So again, everything I'm underlining in red is like a fill in the blank. These are all pretty much the same. And then for the next part, that's going to always, you're going to see is assume for n equals k. That's always going to be there and is true for some k. This part right here comes directly from whatever it is you're trying to prove from up above in part 1. In part 1, you just replace the n's with the k, and you just rewrite it. The next part that's always going to hold true is let n equals k plus 1. That is, and this again is where you fill in the blank, right? So this is the fill in the blank part. That part is basically rewriting part 1, but now you're going to put in k plus 1 instead of k. And then all of this part here, all of this part is where your algebra comes into. And so that's a part is the fill in the blank, it's the work there. When you get down to this part in the bottom here, let me erase this highlighting part. When you get down to the bottom here, in the bottom part of your step 4, what's always going to be the same is since left-hand side, right-hand side, you have to decide whether or not it's an equal sign or an inequality. And then that's going to still be wrote on almost every one of them or something similar. This is the part that you were trying to prove in the very beginning, so you go way back to step 1 and you just write it down verbatim in whatever step 1 had. And then the next part, this is what is going to be true on all of them. So, I mean, you could pretty much just type out the parts in green and leaving the blanks for the red, and just making sure that you knew what goes into the red. Again, you're going to see is by the proof of mathematical induction, we have that. All of that is just, you can just type it out on a sheet, make multiple copies, and then just fill in the pieces that you need to fill in until you get comfortable doing these. This is the part that you put in, and then is true for all, and then this is the part, in this case, we're true for all natural numbers. So all of them have the same pieces, okay? So let's take a look at our next example. So as we take a look at our second example, I'm going to highlight what's the same from previous example and what's new. Proof 4. So that's all the stuff that's same. What's different again is this. This is the new thing I'm trying to prove. And this is where I start. I'm going wild and crazy here. I'm going to do n is greater than or equal to 1, but I absolutely could have just done for all natural numbers, because natural numbers start at 1, and I could have done that, but I want to go wild and crazy. Going on to our second part, notice that let n equal is still the same. The left-hand side is still the same. Excuse me, I'm trying to get over a cold. And the right-hand side is still the same. The only thing that's changed from our previous one, well, it didn't really change on this one, is n equals 1. Left-hand side value is different. And then the right-hand side value is different. Left-hand side is I put in 1 right here, and I got 2. And I put in 1 right here, and I got the 2 to the 2 minus 2. That's my right-hand side, which I'm not quite done with, so let's go a little bit further down. And you can see on the right-hand side is equal to 2 squared minus 2, which is 4 minus 2, which is just 2 to the 1. And so this part And this part is new compared to the last one. But you'll notice that this part is still the same as the last one. So again, you could just get a sheet, everything, or have a green underlined. You could have just typed that part in and just left blanks for the parts that are red so that you can fill that part in. Now we're going to get into the algebra part. So let's go to the algebra part. So we assume this is true for n equals k. Again, underlining what you expect to see in all of them. Assume n equals k is going to be true for all of them, and the statement is true for some k. This is the part that you fill in, which comes directly from here, just replacing wherever you see n, you replace it with k. Here's our algebra part. So this, let n equals k plus 1, notice that is the same. The words that is. And then what's different is this part. This is a part that you fill in. Just like my previous example, you take and you go up to our very first equation here and you just replace, wherever you see n, you replace it with k plus 1. And notice on this one, I also did my previous term. Okay? So if you were to write this all out, everything that's underlined in green will be the same, and all you have to do is just fill in the blanks. Let's keep moving. So on this case, again, I am working on the left-hand side. I write the left-hand side, just the left-hand side. And what you're going to see on the left-hand side is that because I'm using that previous term, the 2 to the k, I get to replace all of the terms from 2 to 2 to the k with what I assume to be true. So this part right here, all of this part, because I assumed it to be true, all of this part I assumed to be true, I can replace with what I assume to be true, and that comes from step number 3, part number 3. Okay, so let's keep moving. And then what I end up with is the terms 2 to the k gets replaced with this part right here, which is 2 to the k plus 1 minus 2. So now let's go ahead and just do some more algebra on that. And what I get is I'm just rearranging it. So I get 2 to the k plus 1 plus 2 to the k plus 1 minus 2. I'm just trying to arrange like terms together. So now I have two. I have two of them. I have this one. I have a second one. So that's where that 2 comes from. All right? So then 2 is just 2 to the 1. So I'm just going to take this 2 to the 1 here. Just write 2 as 2 to the 1. And that way, the fact that I have the same basis, I can add my exponents. And when I add my exponents, I'm going to get 2 to the k plus 1 plus 1. That plus 1 comes from the fact that's right there. Okay? But then what I have, remember, keeping my eye on the prize, is I have the right-hand side. Let's go back up and show what I was trying to prove. Here, what I was trying to prove, this is my right-hand side. I was trying to prove this lovely right here, which I now have. I have my eye on the prize. I got there. So, since, and again, this is the stuff that is the same, since the left-hand side equals right-hand side, then fill in the blank. Notice I go back to what I started out with, and then holds true for n k plus 1, and since we assume that is true for that, that's going to hold true. Everything that I highlight in green, you can just type on a sheet, and then for some reason I just picked up some interesting colors, and then on my box here, my shade, whatever. So by the principle of mathematical induction, we have that. That all remains the same. This is the part that you fill in. Is true for all. And then this is also the part you fill in because that's what they told us where to start. All right, let's take a look at our next example. Now, the first two examples were equals. The next two examples are going to be with inequalities. So I said this side equals this side, and I worked with one side, and now I'm going to do this side is greater than this side, or this side is less than this side, and let's see how that works out. Let's take a look at our third example here where we have an inequality, and we don't start with n equals 1 or n is greater than or equal to 1. So what is still the same, however, is prove that for some n. This is the part that changed. We have the inequality. We're starting at 3, and here's our inequality. So we don't have an equal sign statement. We have an inequality statement that we're trying to prove. But other than that, I mean, pretty much everything stays the same. So what we're going to do is we're going to go ahead and look at our first part. Notice let n equal is still the same, then left-hand side, and then the right-hand side. That's all the same. Parts that are changed is that we start at 3. I put 3 in right there, and I get this part, which is still this part. And then I put 3 in for the right-hand side. I put that in right there. Okay? So that's still the same. And what we have is the left-hand side, the left-hand side is greater than the right-hand side. So this part, and this part's the same. It's just this, in this case, we're going to use the inequality. So a lot of the stuff is still the same. And then we say, this holds true for n equals, the part that changed is 3. So okay, so far on the inequality, everything's still the same as what we had for the equality. Everything is still the same. Let's keep moving. All right. Part 3, assume this holds true for some k. Look, that's still the same. Is true for some k. Assume n is equal to k. The part that changed is this. That's the part that you fill in. And that comes directly from up above. And that is just replacing my n's with k. So instead of having 4 to the n minus 1, it's 4 to the k minus 1. Instead of being greater than n squared, it's greater than k squared. All right. Let's go on to our next part. Notice we still have let n equals k plus 1. That still is the same. The red is what you'd fill in. And that comes from the fact that I'm replacing from part 1, step 1, I'm replacing n with k plus 1. Now you're thinking, but wait a minute, shouldn't it be 4 raised to the k plus 1 minus 1? And the answer is yes, so let's take a look at that. Let me just scroll up a little bit more. It is true. The left-hand side is 4 to the k minus 1 plus 1 is just 4 to the k. That's true. All I did was simplify. Plus 1 minus 1 is 0, so I just get 4 to the k. Now I'm going to break it back apart and say, well, this is where I started. Why did I do that? Well, because I could. All right, now for inequalities, we usually have to introduce more inequalities. It's not as simple as the equal sign. We have to introduce more inequalities. So we start still with the left-hand side, though. So we have 4 to the k is equal to 4 to the k plus 1 minus 1. But for this part right here, let me go to this part right here. I'm going to go to just black. I'm going to go to just black. Just give me a minute, sorry. Just black. So this part right here is I'm saying that this is 4 to the k minus 1 times 4 to the k raised to the 1. And the reason I'm doing that, because the bases are the same, I can break them apart, is because what I know is holding true is that I always want to take the left-hand side and try to incorporate part 3. So what I know is that this part right here is part of part 3. That's that part right there. And then, if I know that's true, if I take this part 3 and I multiply both sides by the number 4, I get this. That is going to hold true. And I'm using part 3 to get there. Okay? Now I'm just going to work with the 4k squared. What I know is 4k squared is the same thing as if I write k squared 4 times with plus between them. Or I write k squared plus 2, k squared plus k squared, because I can add these terms in the middle here. It's k squared plus k squared, and I get 2 of them. There's a reason why I'm going to do this, okay? Now, k squared is greater than k all day long. 2k squared is greater than 2k all day long. And this is for k greater than or equal to 3. Now remember, that's where we had to start. We don't get to start at 1. We have to start at k is greater than or equal to 3, because that's what we're trying to prove. This is a proof for k is greater than or equal to 3. And that means that k has to be greater than 1. So working with just the 4k squared side, we knew that 4k squared is equal to this. So this is what 4k squared is equal to, and then we get it from here, right? Then we know that that individually, piece by piece, has to be greater than k squared plus 2k plus 1, because each piece individually is greater than the other piece. So that has to hold true all day long, okay? Now, this again is just 4k squared. This is still 4k squared. But this side, the k squared plus 2k plus 1, I factor it and I get that. Eye on the prize. Remember, I am trying to prove that, going back up to what I'm trying to prove, I am trying to prove that 4k is greater than or equal to k plus 1 squared. That's what I'm hoping to prove. Okay? So this is part of my eye on the prize. Let's keep moving. Now, what I had was, I'm going to write this in here, what I had was 4 to the k minus 1 times 4 is greater than or equal to 4k squared. But remember, that is 4k squared, which is greater than k plus 1 squared. And with inequalities, you can just kind of almost pretend, if it's a true inequality, that this middle piece isn't there. So I have shown the left-hand side, which is 4 to the k minus 1 plus 1, which is 4 to the k, is greater than or equal to the right-hand side. So going back to what is always going to be in every one of them, since this and this, fill that in, then fill this in, holds true, assuming that this is there. So that's all going to be the same. Let's keep moving. The last piece here is by the principle of mathematical induction. We have that. Look at that. Is true for all. That still holds true. And then the pieces that you put in is this part, which is what we started out with, and then whatever is we got to start for n. Leaving the best for last. So prove that for some n, that's always going to be there. This case, I'm telling you, get to start at 5, and this is the inequality that we're trying to prove for values greater than or equal to 5. Once again, let n equals, then left-hand side, then right-hand side. We start at 5. I put 5 here in the left-hand side, so I get 5 squared. This is the part that I put in. And then I put in 5 in the right-hand side, so I put that in right there, and I get 32. Left-hand side, right-hand side, get your inequality the right direction. This holds true for some n, and the 5 is what you have put in. Let's go on to the next step. Part 3. So assume for n equals k is true for some k. This is the part that you put in as your blank. And that goes from, again, part 1 by replacing the n's with k's. Going on to part 4. That n equals k plus 1. It's always there. That is. This is going to what we're proving, and all we're doing is replacing n with k plus 1. Okay. Now, this is a slight deviation from the previous ones. In this case, I'm not going to strictly just pull the left-hand side. I'm not strictly just working with the left-hand side. I'm allowed to take the left-hand side and subtract the right-hand side, and I'm allowed to take the right-hand side and subtract the left-hand side. So that's what I'm going to do. I'm just going to take the right-hand side, I'm going to subtract the left-hand side. So here's my right-hand side. Now notice I'm not working with any inequality. Just like my previous one, I can introduce them as I go through, but I am not using any inequality to begin with. Okay? Okay. So just like in my previous example, I have 2 to the k plus 1 is the same thing as 2 to the k times 2, because that plus 1 means I have just 2 to the 1. So 2 to the k plus 1 is 2 to the k times 2. And then I went ahead and multiplied out k plus 1 squared. Here is where we put in what we've got from part 3. We assumed that k squared is greater than 2 squared. Or excuse me, k squared is less than 2 squared. All right? So then if I go back to this step right here, or this piece right here, this right here, and I replace 2 to the k with k squared. So what I know is if I take that whole thing, which came from right here, then if I replace 2 to the k with k squared, then this whole thing has to be greater than the replacement with k squared. That has to hold true. All right? Now, just working with this piece. I'm going to come down here and just work with this piece. So 2k squared, I'm going to go ahead and say 2k squared minus k squared minus 2k is equal to k squared minus 2k minus 1. That's the same thing as k squared minus 2k plus 1 minus 2, because we know that 1 minus 2 is negative 1 all day long. The reason I'm doing that, it allows me to go ahead and factor this part, right? So I'm going to factor that part, and there's a reason why I'm doing that. Since k has to be greater than 5, that was what we had to prove in the very beginning. We're proving this thing for k greater than 5. Then if I put 5 in there, because that's the very first number I can put in there, if I put 5 into k minus 1 squared minus 2, then I know that k minus 1 squared minus 2 has to be greater than or equal to my very first term I can put in there, which is 5. So I put 5 in there and I get 16 minus 2, which is greater than or equal to 14, which is greater than 0. And that means that what I have is 2 to the k plus 1 minus k plus 1 squared has to be greater than k minus 1 squared minus 2, which has to be greater than 0. And just like before, I can drop out this middle piece right here with my inequality, because my inequality has to hold true. And that means that 2 to the k plus 1 minus k plus 1 squared has to be greater than 0, which means that k plus 1 squared is going to be less than 2 to the k plus 1. And this is where we always put the same stuff in. Since this and this then holds true for that, assuming that. So the only places that you have to put in information is this and the inequality in this case. All right? So then my very last statement is, by the principle of mathematical induction, we have that is true for all that n, and you just put in that piece and you put in the greater than 3. All right? So there are 4 examples of proof by mathematical induction. I would recommend that you print out or at least take really good notes on this. So in class, when we do the homework in class, you have at least exposed yourself to the steps that are the same on every single proof by mathematical induction, give or take, so that when we're working on the stuff in class, you will have like a template or a guideline on how to do these. Thank you for watching, and I'm looking forward to seeing you in class.